Okay, so this is section 9.5. Save that. Maybe it's taking forever. And apologies, because as I said in the last video, I'm still sick, so sorry. Okay, so you know why we find series. You know some tests to see if and where a series converges on intervals, so you can find the radius of convergence. But you also have to know the intervals of convergence. So we have to test endpoints. And there are multiple tests that we are going to use to get this job done. The first test is the P series. So if I have 1 over n to the P, the series converges if P is greater than 1 and diverges if P is less than or equal to 1. Okay, so that goes with my harmonic thing that I talked about yesterday, which is the harmonic series, which is just this series for 1 over n. That's a P series with P equals 1, but this is a special one. They gave it a special name. It has harmonic properties. Okay, so let's do 2 examples of these first. So I have 1 over n to the 3 halves. Now, you don't have to write it like this, but I just wanted to give you the heads up. You might see it like this. You would probably be more likely to get this and expected to realize that that is the same thing. And I would write the series converges, convergent P series, P equals 3 halves, and P is greater than 1. Make sure you make it very clear you know what the P series is and what the stipulations are. Okay, then this is a divergent P series. P is equal to 1/2. This is n to the 1/2. And P is, excuse me, less than 1. So this series diverges. And here is our harmonic series. Let's talk about why this series diverges. You don't have to have this in your notes. I just want you to think about it. Okay, so this first term is 1, then the next term is 1/2. The next 2 terms add up to a number that is bigger than 1/2. The next 4 terms add up to a number that is bigger than 1/2. The next 8 terms, bigger than 1/2. The next 16, the next 32, 64, 128, all add up to numbers bigger than 1/2. So basically, I'm adding 1 plus 1/2 plus 1/2 plus 1/2 an infinite number of times. So that gives me, I don't have the sum. And there are other ways we're going to test 1 over n later, but that's it for now. Okay, this goes back to that stupid bartender joke that we did in the beginning, but this one's different because it's the first one orders a beer, the next one is 1/2, 1/3, 1/4, 1/5. And then the bartender yells at them, but wouldn't he get rich selling an infinite amount of beer? Like, how would it ruin him? He would just be selling so much beer. It doesn't make sense to me. Okay. Now we're going to learn this in kids. I can't get adults to understand this sometimes, so don't freak out. Okay, so I have the series 1 minus 1/4 plus 1/9 minus 1/16. Okay. If the question were just to say, does this series converge? The answer is yes. The terms alternate, they decrease, and they approach 0. So this is a convergent series. But that is not how they're wording this question. Is the following series absolutely convergent, conditionally convergent, or divergent? Okay, so I know that this is the series, the one that they've given to me here is this series down here. But it does not matter how they give me the original question. It doesn't matter if they give it to me alternating first or if they give it to me not alternating first or alternating. I did that in reverse order. It doesn't matter if they are asking about absolute convergence. And again, if they were to say, does this series converge? The answer would be yes, P series, P is greater than 1, convergent. Is this series convergent? Alternating series test, terms alternate, decrease, and approach 0. Yes. But because they asked about absolute versus conditional versus divergent, I know divergent isn't even on the table because I know 1 over n squared is convergent. But here we go. No matter how they ask the question, you check for absolute convergent first. Always. And that is the series n equals 1 to infinity, 1 over n squared. And again, coming down here, the first thing I'm going to test is this. And in both cases, because the question is different, looks different, but it's exactly the same, this series converges. P series, P equals 2, P is greater than 1. So this is a convergent series. So because the positives are convergent, the positives are convergent, this is absolutely convergent, no matter how it is worded. And I'll have kids say, but they're giving it to you as an alternating series. I don't care. The first thing I'm going to check is to see if the positives will converge, and they do. So this series is absolutely convergent. I don't need this series to alternate in order for it to converge. If in the event you get a series that has to alternate, then we say that it is conditionally convergent. Don't use the word it. We say the series is conditionally convergent. But in this case, this is an absolutely convergent series. It does not matter how I initially present it to you. Okay, is the harmonic series absolutely convergent, conditionally convergent, or divergent? Again, you have to show that you're testing for absolutely first. So that's n equals 1 to infinity, 1 over n, divergent P series, P equals 1, which is P is less than or equal to 1, the series diverges. That's the test. Now I'm going to check for conditionally convergent. I am going to make this series alternate. I don't care if the first term is positive or negative. If the series alternates, does the series converge? Let's see, I plug in 1, I plug in 2, I plug in 3, I plug in 4. Yes, convergence. I don't think I need to put that yes there. Terms alternate, decrease, and approach 0. And you don't have to say this is the AST. You can, but you're not required to. But you just have to say why we know this converges. So because the series converges, if I make it an alternating series, this is a conditionally convergent series. Okay, here we go. Checking for absolute first. This is diverging. Now I'm going to see if that is not what I meant to write. It's not on drugs, I swear. Well, technically, I'm on cold medicine. So then I check for conditionally. By the way, what I did is a common mistake. You can't get away with it. I'm just teaching, so I can get away with it. Don't do it on a test, mine or the AP. Okay, so let's see, the terms would be alternating, terms alternate, decrease, and approach 0, right? No matter what I put in for n, the numbers are getting smaller and smaller and smaller because 1 over a giant number is getting closer to 0. So this is convergent. So this series is conditionally convergent. Again, you have to check for absolute convergent first. Okay, again, pause, see if you can get this on your own. I'm going to go ahead and start doing it. This is the series n equals 1 to infinity, the natural log of n over n. So I'm going to check for absolute first. And I know that this series is greater than the series n equals 1 over infinity, 1 over n. Since 1 over n is divergent harmonic. N equals 1 to infinity. The natural log of n over n also diverges. So you want to show that this is true, and you want to talk about 1 over n diverging. Okay, this is going away. Now the next question is it conditionally convergent? If the alternating series converges, then does that series converge? And the alternating series is n equals 1 to infinity, negative 1 to the n, natural log of n over n. Yeah, if you need to, if you didn't see that, you could take the limit as n goes to infinity for the natural log of n over n. Use your L'Hopital's, and you're going to get that the terms approach 0 and they are decreasing. So this is another conditionally convergent series. Okay, so now we're ready to test some endpoints. So they're asking me, they want us to find the derivative of this, but we have to find out where the series converges first. If the series doesn't converge, why would we find the derivative? No point. So the first thing I'm going to do is run the ratio test. So the limit as n goes to infinity, I have absolute values. Do not put this inside of absolute values. I will take a point off for it. Just don't, because we're dealing with absolute values, so I don't care about the alternating part. So I'm going to have x to the 2n plus 3, which is x to the 2n times x cubed, over 2n plus 3. Everywhere I saw n, I put in n plus 1. And that's going to be 2n plus 1 over here, x to the 2n and x. These are gone. These are gone. 2n over 2n is gone. And x cubed over x gives me the absolute value of x squared. I need x squared. I didn't need the absolute values because that's always positive. There are no more n's in here to even work with. Okay, so I need x squared to be less than 1. We talked about that during the pre-calc review. For that to happen, x has to be between -1 and 1. Okay, you need to show this internal. Do not ever touch this again. Do not touch this again. Okay, so now you're going to check endpoints, and you're going to take this x is -1, and you're going to go all the way back to the original problem. And in the original problem right here, you're going to put in -1. And then you are going to simplify. It's too far. And then when I plug in my -1, that's going to, if I clean this all up, I get -1 to the 3n, that 2n plus 1. That's just the harmonic series, right? It's just another form of that harmonic series. Now I have to plug in from the other side that n equals 1, or that x equals 1. So I'm going to start over and plug in x is 1. And when I do that, I get this. So you're ready to be done. I'm going to get this kid started for the test. Okay, so then take notes. I'm going to come back here for a second. Right now, I would, after I do this work right here, I would rewrite -1 is less than or equal to x is less than 1. Okay, I do not touch this again. Do not. You get 1 point for having this, but if you put this in and it's wrong, you lose a point. So have your internal part, show that first. And now we're going to do this one, and then we do the next one, and it's also the harmonic series. And now you would add the other equals. Okay. And then the question wanted us to find the derivative. Do so. And when you're finding the derivative, remember, you're just swinging the exponent down in front, subtracting 1 from the exponent. Same thing you've always done. And then clean it up. If they ask you for some terms, do it. Okay, the integral test. And I have people who struggle with this one as well. Okay, first thing you always have to check is that it's a continuous positive and decreasing function. You must write these stipulations if you're doing the integral test in a free response question. If you don't do that, you miss one of the points. Okay, so you're going to take the integral of whatever your f of n is, your f of x, from 1 to infinity. Actually, you could do 100 to infinity. Like 1 to infinity is going to keep you from standing out, which is good. But like when we're doing this integral, it's not telling us what the sum is. It's just telling us if we can find the area under the curve for this equation, then I can find the sum also. So if I get that there's actually a value to this improper integral, then the series converges. If I get that this limit is infinity, when I find this limit using improper integrals, then they both diverge. Okay, now, as soon as I see this, I know what the answer is, but they want me to prove this using the integral test. I'm telling you, if I have this, let's say the sum of this is 6. I don't even think it's 6. I think it's like 2. So if like I have infinity minus nothing, right? So I know this one is going to diverge. But they want us to find the integral. So I'm going to take the limit as, I'll use b. b goes to infinity from 1 to b for 1 over n minus 1 over n squared dn. If you want to use x's, if you're more comfortable using x's, go ahead. So I have this all worked out. I used n's, obviously. Since I get infinity as my limit, I shouldn't have that arrow there. The series divergence. Okay, limit comparison test. There's three different tests. Technically, I think there's 2, and I'm going to show you what I mean. So what I really think that this series, there's so many ways to do this problem, but we're going to do what they want us to do. I really think this looks like 1 over n squared, right? And that's what I'm thinking in my head. I don't write that down. But I would write down, I might write this down and say convergent P series. P equals 2 greater than 1. The test that you use is this. Your unknown series divided by your known series. And again, I usually skip this step and multiply by the reciprocal. Gone. I get 1 for this limit. As long as you don't get infinity, you can get anything except infinity, the series converges. So I would write both converge. Okay, I took an unknown divided by a known convergent. If you get anything besides infinity, your series converges. Here is the exact wording of the problem. And technically, it could be this. There could be an equals there. Again, the book says there are 3. I think of it as 2 tests. Okay, if I take an unknown divided by a known, and I get anything except infinity, the unknown converges, as long as that bottom one converges. Okay, now for this one, I'm going to compare this one to 1 over n squared. And some people would say, why don't you compare it to 1 over x n cubed? And I probably would, but this is a different test, and I want to show this to you. So I'm going to take my unknown divided by my known convergent. This is a p series p equals 2 greater than 1 convergent. And when I do this, I get 0. So again, it falls into what I said before, which is if I get anything that is not infinity, when I have a convergent series in the bottom, the top one also converges. And that's the specific test. But again, I combine all of that into the first test. And here's your third one. I think this one looks very much like 1 over n, which I know diverges. Divergent harmonic. And when I do this math, I get infinity. If you get anything besides 0 when you're using a divergent series, then the unknown diverges. So this one diverges. If you take an unknown divided by a known and you get anything but 0, your life is good. So there's a ton of examples for the first one. For this, I just compared it with 2 over n. You could have used 1 over n. It doesn't matter. I think I did. I did change it to 1 over n. And when I do this limit, I get 2. And when you're comparing to a divergent series, anything but 0 is good. So the unknown also diverges. Now, in my head, I'm thinking this is just 2n over n squared, which is 2 over n, which is just the harmonic series. But you got to show a little bit of work if they ask for it. This one, I think, looks like 1 over n squared or 3 over n squared. But I'm going to compare it to 1 over n squared. That's a known convergent series. The series p equals 2 greater than 1. When I do this reduction, I get 3. So since I did not get infinity, the unknown also converges. Sine of 1 over n. I think that this one's oscillating and that it's going to diverge, but I'm not sure. I'm going to compare it to 1 over n, which is a known divergent series. So I want anything except 0. I use theta substitution. And I get 1, and that's all I need. I did not get 0, so this series diverges. Okay, so now this one is a little bit tough. There's going to be multiple parts for this one. I want you to pause. I'm going to have all the work here, but I want you to see if you can get it. Run the ratio test first. Hit pause. So if you get all this work, you'll have that as your interior. Now you have to start over and plug in -4 wherever you see x. And you're going to start over and plug in 4 wherever you see x. So this is our interval of convergence. Okay, interval of convergence. Now I'm going to ask you some more stuff with this question. So I'm working with this interval only. Only this interval. I will consider no other points. So they ask, where is the series absolutely convergent? On the interval, on this interval, where is the series absolutely convergent? Well, right away, I know that I'm convergent from -4 to 4, but I need to look at that endpoint -4. Why was I convergent there? And I'm going to come back here and look at -4. What was that test for negative? There we go. Now, this is, if I took away this alternating part, this would just be the harmonic series. N over n squared is 1 over n. So we're not converging at that endpoint, absolutely. So this is, oops, this should be a 4. So this is the only place where I am absolutely convergent. That's always the interior, but you have to check those endpoints to see why you were convergent there. Now, the only one I can go back in and look at is -4. At -4, this series converges conditionally, because if the series is alternating, then the series converges at -4. So our interval of absolute convergence is -4 to 4, conditionally convergent only at -4. Okay, we don't look at 4 again. That's not in our convergent region, so I can't look at 4 again. Okay, so where does this series converge? Where does it absolutely converge? Where does it conditionally converge? 2 ways to do this problem. I can either use the ratio test, and when you use the ratio test, you have to show that you're testing the endpoints. There are no exceptions to this. You have to, if you're running the ratio test, show that you're testing the endpoints. Now, where does this converge absolutely? Well, I only have these options. So this is absolute convergence on this interval, because that's what I got from this. And there are no other points for me to consider. So that it is not conditionally convergent anywhere. Now, the second way that you could do this problem is this is a geometric series. And the geometric series, we never have to test their endpoints. Our radius has to be, our r has to be between -1 and 1. And that means that I have to get x in here, take the, I have to exponentiate everything. So that gives me my interval. You do not have to check endpoints when you have a geometric series. And that is it for section 9.5. Watch that section as many times as you need till it's all sunken in.